Today's talk is less tutorial, although, of course, if there are any questions, please feel free to stop me. And it's more about research that we've pursued in my group over the past 10 plus years at the intersection between convex optimization, this thing that I mentioned yesterday, and graphs. And I'll talk about some mathematical ideas, but also describe some applications. Okay. This is, again, like I said, if there are no questions, this might take me an hour. So please ask questions so that it'll take me 90 minutes. So graphs obviously show up in tons of applications, and in particular, structural properties of graphs in each of these applications are really play a prominent role. A prominent example of graphs is in biology, where depending on the kind of structure you see in your graph, you can actually obtain insight about some biological function. If the graph, for example, is a gene interaction network. Graphs are, interestingly, also used in chemistry. This was new to me. I only learned about this in the context of our project, one of our projects that I'll describe later, where molecular structure is described or coded up using a graph, and comparison between two molecules is conducted by comparing two graphs. So that seemed new to me, but that's apparently a popular way to think about structure comparison in chemistry. A topic that I've worked on in the past concerns the use of graphs in statistics, where statistical models are described using graphs. These are things where the nodes of a graph represent random variables, and the edges describe statistical dependencies among these variables. So graphs show up in tons of situations, as you might expect, but what's interesting is the way in which the role of graph structure comes in each of these applications. Okay? I want to describe, before I describe sort of a way to think about linking convex optimization graphs, I want to describe problems that I have in mind for which we want to develop solutions based on convex optimization. Okay? And these problems I'm broadly characterizing as inverse problems involving graphs. Inverse problems meaning you have an underlying graph of interest, you have some corrupted or partial information about this underlying graph, and you wish to reconstruct or obtain that underlying graph in some fashion. The classical notion of an inverse problem. Okay? So here is one example. It's a prominent example. Lots of communities have studied it. It's called the planted subgraph problem. It's one where you have a small graph and a big graph. And the question is the small graph a subgraph of the big graph? It shows up in the context of biology and gene interaction networks, where you have some large network typically gathered from an experiment, from experimental data, and you want to identify small subgraphs, maybe whether they occur in a large graph, how many times they occur in a large graph, and so on. And the reason this abstract question is of interest in a biological context is because the small graph might actually specify some known biological function, and you want to see whether that known biological function is in some way manifest in some larger gene network that you gathered data about. Okay? So here is a simple example. This is a graph on 16 nodes. It's called the Klebsch graph. We've planted it inside a graph on 50 nodes, where the blue edges are the Klebsch graph, corresponding to the 16-node graph, and the other red edges are noise, and you wish to be able to identify which nodes here and which edges here correspond to this smaller 16-node graph. You're given this, and you're given this, but if I did not color code the edges for you, it's not an easy question to try and figure out where this thing appears inside this. Okay? So that's the challenge. And this problem is NP-hard in general. And we all know what this means. We're in the CSA building, right? So this means that in the worst case, you should not be able to expect to solve this problem in a computationally efficient way. Okay? At least modulo some big conjectures. Okay, I described briefly molecular structure comparison via graph similarity. Here, the mathematical abstraction is that you're given two graphs, G1 and G2, and the question is, what is the smallest number of changes you can make to one of the graphs to get to the other graph? And changes here involve vertex deletions and additions, edge deletions and additions. You can kind of, enforce different kinds of costs on vertex deletions or additions versus edge deletions or additions. Lots of variants of this, but this is the conceptual problem. And so if you have G1 and G2 given to you like this, to go from G1 to G2, first you might remove this node and this edge, and then you might add a new edge here. That's what this represents, and that's how you go from G1 to G2. So in this case, this turns out to be the smallest number of changes you can make to go from this G1 to this G2. But this is a small example, of course. In general, this is also an NP-hard problem, so we shouldn't expect to be able to solve this also tractably. But again, it shows up in a ton of applications. Lots of pattern recognition type problems are formulated this way, but we'll see some examples with molecular structure comparison. Graphical models. These are, like I mentioned briefly, statistical models defined over graphs, where the nodes or vertices represent or index random variables. The edges specify statistical dependencies among the variables. And a question of interest, so these are, for example, this is a graphical model involving 7 variables. And the goal in the learning in the graphical model selection problem is that I give you observations of these 7 random variables, and you want to identify or fit a graph that best models the statistical dependencies among these variables. And the kind of graph structures that are viewed as tractable in the graphical models literature are graphs that maybe have low tree width, that are planar graphs, graphs that are sparse, that have very few edges, and so forth. And again, this is a hard problem in general. So these are the kinds of questions for which we want to develop a solution framework based on optimization. Okay? And all of these have the characteristic of inverse problems over graphs. There's an underlying graph that I wish to reconstruct, and I have some partial or incomplete information about it. Yeah?
So one question.
Yes, please.
So, what is the data that is available to us to construct this graph?
Good question. So most commonly, you're given, so imagine you have a vector of, random vector of length 7. You'd be given observations of this random vector. There are variants of it where the observations might be, might have missing entries. And so you can imagine all of those sorts of elaborations, but in its most sort of basic form, you're given observations of a random vector of dimension 7, and you want to figure out what the underlying graph.
So there could be another problem where you know the graph and some of the entries you want to recover other. That's a different problem.
You could imagine that fitting within this sort of paradigm also, which is,
because we are given a graph and some of the entries.
I would call it an inverse problem because, the object of interest is a graph. You're given partial information about it in some fashion. Good. So, actually, this is the application about which I'll be saying nothing today. I'll be saying a lot more about the other 2 applications, but still graphical models are very cool and interesting, so let me say it. So this graph represents the following statistical property, that if you look at any 2 variables, i.e. nodes, that do not have an edge between them, the statistical relationship implied by that lack of an edge is that the variable at node 6 and the variable at node 7, these random variables, are conditionally independent when conditioned on all the other variables. And if there is an edge, Even after conditioning on all the other variables, there's still some residual dependency. So that's what edges mean. In this context, the edges are often weighted, which would give you, how much dependence and so forth, but yes. So what's difficult about these problems? What's difficult about these problems is that the kinds of graph properties that we wish to reason about involve properties of unlabeled graphs, meaning that when I tell you I want to reconstruct, I want to figure out whether this copy of a small graph is inside a big graph. If I relabel the vertices of the small graph, the underlying question doesn't change. It's invariant with respect to that relabeling. So I'm really reasoning about properties of unlabeled graphs, and that automatically introduces a kind of combinatorial complexity to the problem. Right? So that's really the core reason why all of those preceding problems are NP-hard. Of course, not all problems where there's combinatorial explosion end up being NP-hard, but that's really the reason why in these cases they all are. And so the proposal today will be a solution framework based on continuous optimization, in particular convex optimization. And we'll define this notion called a convex graph invariant. A graph invariant is a property or parameter associated to a graph that does not depend on the labeling of the vertices. So if I tell you, here is my graph, this graph is a tree. That property of the graph does not depend on how I label the vertices of the graph. Such things are called graph invariants or graph parameters. We'll talk about graph invariants or parameters that additionally are convex. So what that means, when is it meaningful to even talk about convexity? Convexity is a property, like we discussed in the previous lecture, that's defined over Euclidean spaces. Graphs don't naturally you don't typically think of them as objects in the Euclidean space. And so all of those are things we need to understand and resolve. And I'll talk about progress in two of the model problems, the first two that I described, planted subgraph and graph at a distance. Okay? All right, so when we talk about properties of graphs, structural properties of graphs, properties that do not depend on the labeling of the vertices, we typically talk about them using what are called graph invariants. I could tell you that my graph has some chromatic number or some diameter or some girth or some spectral properties or some degree distribution. These are all properties of graphs that do not depend on how the vertices of a graph are labeled. Okay? So for example, this graph here is planar. Planar means that I'm able to draw the graph on a plane in such a way that no two edges cross each other. So the fact that this graph is planar does not depend on how the vertices are labeled. You call this 1 and this 2 and so on, but it doesn't really matter. Right? So it's such properties of graphs that we're really referring to when we talk about graph invariants as structural properties of graphs. And this is really the key thing we need to be able to deal with, because this is the key source of complexity in all of those inverse problems. Okay? So, suppose we were to try to write down a convex approach, a convex relaxation, to solve the planted subgraph problem. How would this actually go? And let's see where we first hit a stumbling block. And then we'll develop our framework to resolve that stumbling block. Yeah. You could ask questions like, how, are nodes 1 and 5 connected? And that would really depend on, which vertices you're calling 1 and 5, right? Yeah. That's a simpler example. But everything else that I'm talking about does not really depend on how things are labeled. Right? Okay, so let's try and develop a convex solution method for planted subgraph and see where we hit our first stumbling block. Okay? So again, planted subgraph is you have a small graph instead of a big graph, and you want to figure out where the small graph is in that big graph. So the small graph I'm going to call H. It's a graph on k nodes, And I'm going to represent this graph using a k by k symmetric matrix. So Sk is the space of k by k symmetric matrices. It's the adjacency matrix of this graph. This is not unique. There are lots of adjacency matrices that could represent the same graph, right? That's one of the sources of complexity that we're going to have to deal with. But let's pick one. I've picked this one. And similarly, an adjacency matrix for my larger graph G. And I'm going to search over all n by n matrices, symmetric matrices, to maximize the inner product between my graph G and this matrix, to maximize their alignment. Subject to, I want this thing to look like the small graph, right? I want it to be exactly zoning in on where the small graph is. That's what I want X to look like at optimality. So I'm going to ask that Xij be 0 if G itself has no edge at a particular location. And the key source of complexity is that X belongs to this set. So I have the adjacency matrix of H, zeros everywhere else, so I've padded it so it becomes an n-node graph, right? But the particular adjacency matrix that I have may not be the right way to view where the small graph H lives inside the big graph G. So I've got to consider all possible relabelings of the nodes of H, and that's what this does, right? I multiply by a permutation matrix on the left, the transpose of that permutation matrix on the right. That's relabeling the vertices, shuffling the rows and columns, and end up with this. Good? So the first solution approach you would write down, convex, not convex, whatever, would look like this, right? Yeah?
If you don't have the first constraint, what is the problem?
Yes, you could get away with not having the first constraint, but if you think about it, if you have, the first constraint helps you deal with subgraph versus induced subgraph type issues. So I did not want to have to deal with that, and that's the reason I have the first constraint. But in principle, at a cartoon level, just the second one even should be good. But that's the reason I have the first one. Yeah?
What is an adjacency matrix?
Adjacency matrix of a graph is simply a symmetric matrix where you label the nodes of the graph from 1 to k in this case. And the ijth entry is equal to 1 if there is an edge, and 0 otherwise. So I'm not sure I understand the question. AH is a fixed matrix.
Yes. So,
And I'm looking at all possible relabelings of the nodes of it, yeah?
So that forms a set of all a different.
All possible n-node representations of this k-node graph.
okay.
All possible ways, right? You could say, okay, based on what we talked about the last lecture, what's the key source of difficulty here? This is a linear function, that seems easy. This is an easy subspace constraint. I say some entries of my X have to be 0, it's fine. But this set, has, some sort of combinatorial complexity, and I replace it by the convex hull of the set. Okay, I can do this, and it turns out that if H is in fact a subgraph of G, and this is where subgraph versus induced type issues could come up, hence I have this other line. But if in fact H is a subgraph of G, then this is exact, meaning that I don't lose anything by having stuck in convex hull here as opposed to taking a look at that set. Because I want to maximize alignment. I want to figure out what the labeling of the nodes of H should be inside G so that they're maximally aligned, with the idea being that if they're maximally aligned, that should be precisely when H sits on top of the actual subgraph inside G that represents H.
So in the planted subgraph problem, do you want to give a yes/no answer that indeed it is there, or do you also want?
I want to give a certificate. I don't just want to say yes, but I want to say yes, and this is the labeling of the nodes that will witness H for you.
And is answering yes or no easier than finding?
Answering yes or no is in general also NP hard. So yes, for general H and general G, it's NP hard. But even if I prove for you that, even if I give you a sort of a promise that H is planted inside G, finding where H is inside G is also a hard problem. So yeah, There are lots of sources of difficulty in that question. Yeah.
If H is not a subgraph, then the previous program will still find the maximum matching.
Correct. Some sort of maximum alignment, but you can see from that alignment that it actually is not. So yes, yes.
But in that case, if it's not a subgraph, then this one will not work.
This one will not. Yes, yes, yes. I mean, it will do something, but
There may be some noise you can assume then.
correct,
you can
correct.
do some H. So that first one.
That one will work, but the second one may not. Precisely. So I am thinking really of H being planted inside G, and the thing I care about is where H is inside G. Yeah. There's another question. Yeah.
The agency matrix is kind of real valued entries or it's just one or zero?
Good question. H and G I'm thinking of as unweighted graphs. So A will have 0 and 1 only. But when I write down this optimization problem in particular, I'm thinking of the optimization as being performed over n by n symmetric matrices, and those are real symmetric matrices. When I take convex hull and so forth, it's a real symmetric matrix. But when I say exact, what I mean is that you will get a solution that has only 0 and 1.
So other way of saying the last line is the optimization solution would be at the corners.
Would be at a vertex, yes, precisely. Yeah, yeah. A vertex of a polytope, not vertex of a graph. Yes, yes, that's right. Yeah. Any other question? Okay. Good. So we got from a problem with a combinatorial constraint to nominally a problem that's a convex optimization problem, right? Linear objective, linear constraints, and a convex set. This is convex optimization, but it's still intractable in general. And this is one of the points we made a couple of days ago, that obtaining a convex problem is in general not a big deal. Whether or not it's easy is a big deal. And this in general is hard. Okay. Let's write down again a cartoon sort of formulation for graph edit distance. I'm going to take two graphs, G1 and G2, on n nodes. Their adjacency matrices, pick any particular adjacency matrices, will be these. And for simplicity, I'm only going to consider edge additions and deletions, no vertex changes. We can accommodate vertex changes too, but let's leave that aside for now. Let's write down a formulation again. Yeah?
So in the previous thing you said it's in general hard, but I thought this constructing this convex hull seems easy, right? Because you move a edge.
Correct.
So constructing the convex hull doesn't seem hard. So
No, it is. I mean, so both writing down the convex hull, because there are n factorial many points in this, taking the convex hull of such a large set in the space of n by n matrices, that's difficult. But moreover, I mean, that by itself is not the only source of difficulty. If, let me state it in terms of proof by contradiction, right? If this were easy, then you'd be able to solve planted subgraph in the yes situation where there is a planted subgraph. You'd be able to identify exactly where H is inside G in general, right? So you should not expect this to be easy in general, right? Yeah.
Could you elaborate the second last phrase? Eject if H is subgraph. Why it's...
So I just have a small graph H and a big graph G, and you can write all this down.
Yes.
But whether this convex relaxation has no loss relative to this combinatorial problem, that is the case only when H is a subgraph of G.
So?
I can prove it for you. I can do it offline, but I would rather not do it right now. But yes, yeah, you can write down an elaborate proof for it, and that's why the second line ends up being needed. Yeah. Yeah. Okay. Yes.
When we say it's convex, okay, the objective is linear and the set is convex, but is there a existence of a minima firstly?
Sure, because this is a compact set. This is a bounded set, so okay. Well, just because a problem is convex, we said 2 days ago all problems can be reformulated as convex problems, right? So right then you should know that not all problems are easy to solve. Gradient descent, not all convex problems are easy to solve. Gradient descent, number one, is applicable to unconstrained minimization. Suppose you were wanting to so this is a constraint problem, number one. Number two, even if you were trying to minimize an unconstrained, minimize in an unconstrained way a convex function, it's unclear. You can say, oh, gradient descent will get me there because local minimizers are global minimizers. But that doesn't say anything about whether a gradient is easy to compute. I can write down for you functions that are infinitely differentiable that are convex, but where the gradient is computational, it's NP hard to compute the gradient at a given point.
Well, gradient would be easy because it's linear and you
No, but this is a constraint problem. I was specifically referring to an unconstrained minimization problem. You cannot project onto the set because it's a hard set to project onto.
that
Yeah. But if you were wondering about unconstrained minimization, you are not going to, in general, be able to compute gradients, even of a convex function. You're assuming you have access to gradients.
In a projecting gradient descent setting, projection is the hardest step.
Yes, definitely. Yes, the objective is linear, but projection is hard. Yeah. Even if gradients are available to you, it's not trivial to show for a given problem that you'll converge in polynomially many steps to a desired accuracy versus exponentially many steps. So all of those are issues. So just saying gradient descent is part of the answer, but not the whole story. Yeah. Good. All right, so this is a graph edit distance problem. For simplicity, we'll only consider edge deletions and additions. And what I'm going to do here is fix the adjacency matrix of the second graph, search over all possible adjacency matrix representations of the first graph. I can pick one, or an arbitrary one, and then shuffle the rows and columns, right? Relabel the nodes. Look at the error, and then sum up the absolute values of this error matrix. The error matrix will have 0 if the edges match up, -1 if it's a deletion, and +1 if it's an addition. And you just sum up the absolute values, and this will give you the graph edit distance. Good. You can, in principle, write down again the objective function is a convex function, sum of absolute values. This is a linear equation. You can take the convex hull of the set again. In this case, this is exact. You can prove that this will, under no additional assumptions, actually give you the graph edit distance between G1 and G2 by solving this convex optimization problem. But it is also intractable in general because of the same complexity associated to describing that convex set. Because I don't want to double count. That's all. Because these are symmetric matrices. That's the only reason why. Yeah. So in both cases, for expected reasons, we end up with convex problems that solve the problem that we originally care about, but we're left with difficult sets that look like this. Right? So that's the key challenge. So writing down something convex is straightforward. I told you I would show you the proof of that planted subgraph thing offline, right? It's not a very difficult proof. So actually writing these things down is relatively direct. It's maybe a half page or a page to show that they are exact. But the key source of computational intractability is sets of this form. I give you a graph represented by some adjacency matrix. You're looking at all possible adjacency matrices that represent that graph and take their convex hull. We don't have good ways in general of describing such sets. If we could, P would be equal to NP. So this is the key source of intractability. And if we can sort of make progress on this, understand this better, then we'd be able to plug into the previous formulations that we had and get good convex relaxations. Yeah?
So for any leveling invariant property is the same problem.
This is exactly this. This is the central issue, right? Yes. And it's not a surprise. I mean, it's all possible adjacency matrices. If you remove the convex hull here, this is all possible adjacency matrices that represent a given graph. And you're taking their convex hull because you want to live within the framework of convex optimization.
So in previous problems, both objective and constraints were linear.
Linear with the exception of this.
Yeah. So even for other problems where this leveling invariant property is there, if we can write the objective and constraint linear, this is still the main.
This is still the main sort of issue. In graphical model selection, for example, the objective tends to not be linear, but it'll still be convex, given by negative log likelihood or something like this, and it'll be often not difficult. Sometimes that's the source of complexity too, but this is again the key source of difficulty. Okay, so this is the key source of intractability. The question is, how should we approximate such sets, right? This is the big question for us. And the two things to keep in mind, number one, it's a bit of a constraint, is that we really want approximations that are hopefully convex. We got down to something convex, let's preserve that property. But in particular, convex sets that are closed under conjugation by permutation matrices. Meaning a convex set where if a matrix belongs to that set, conjugating that matrix by permutation matrices also belongs to the set. Okay? So that would be a nice property to have because that's really inherent to the kinds of challenges that we have with these graph problems. That's a constraint on any kind of relaxation we would write down. A source of potential strength is that the approximation can actually be tailored to the particular graph at hand. Which approximations work for which kinds of graphs is really actually, in the big scheme of things, an open question, but we'll have specific instances of certain kinds of approximations that work really well for certain kinds of graphs. But this is a source of strength, something you can potentially use to your benefit. Okay? But this is what we need to sort of understand as we make progress on this question. Okay? All right, so we now have the central definition, if you will, of this talk. A convex function. Convex functions have to be defined over an underlying Euclidean space. Our Euclidean space is n by n symmetric matrices. A convex function that is invariant under conjugation by permutation matrices, meaning that for any symmetric matrix, you have this condition holding for all permutation matrices, will be called a graph invariant convex function. These are the functions, these are the convex functions you want to use in convex relaxations for hard graph problems. You can write down a set analog of things too, which is that a convex set that is closed under conjugation by permutation matrices, meaning that if A belongs to the set, pi transpose also belongs to the set for all possible permutation matrices pi, these will be called graph invariant convex sets. Okay? These are the kinds of objective functions, these are the kinds of constraint sets. And if you take sublevel sets of graph invariant convex functions, you'll get graph invariant convex sets. This is the usual mapping between functions and sets that we see in convex optimization. Okay? So we want to write down graph invariants that look like this. So what are some examples? The maximum edge weight, or the total weight of all the edges, these are convex graph invariants. If I tell you the fifth highest weight edge is something, is that a graph invariant? Does that property depend on the labeling of the vertices? No, so it is a graph invariant, but it is not a convex graph invariant. But the largest edge weight, if you're thinking about weighted graphs, say, is a convex graph invariant. So the convexity condition does impose restrictions. Not every possible graph invariant, as you might expect, is a convex graph invariant. So we need to be careful about the ones we decide to use. Right? Similarly, if you have weights on the vertices, you can write down convex invariants that are functions of those things. You can look at the maximum weighted triangle. That's a convex graph invariant, or other subgraphs. You can look at the second smallest eigenvalue of the graph Laplacian. This is a concave graph invariant. It's a negative of a convex graph invariant. So you can do all these sorts of things. But we have to be careful. We can't just use arbitrary graph invariants. So this is the way you should be thinking if you want to write down relaxations, convex relaxations for graph problems, right? Which ones are useful or not depends on context, but this is what you want to begin with. So let's do some more interesting ones. If you fix for any a, consider the following function of a. We're calling this the sorted degree sequence. By that I mean take a, multiply by the all ones vector, and subtract off the diagonal if you want to. Right? That gives you the degrees, the weighted degrees of all of the nodes of a, of this graph, and sort it. Just put it in ascending or descending order. That's what DA. So consider the following set now. All possible n-man matrices where the sorted degrees is equal to the sorted degrees of whatever a you fix. You fix an a, and you do this. The convex hull of all of these things is a graph invariant convex set. Question 1, is it convex? Yes, by construction, because I'm taking the convex hull of something. Is it graph invariant? That requires a simple check. You can kind of go through this, but it's true also. Okay? And what's interesting is not only is the set a convex set, but it actually has a tractable description using linear programming. So that's actually important if we want to use this set in the context of an actual convex relaxation that we would want to solve, right? Like we saw a few slides ago, writing down a convex set is not the difficult part. It's writing down a tractable convex set that's difficult. And this one actually has a tractable LP description. You can do the same thing with eigenvalues. It's a little bit more exotic and interesting. You know, for any a, let lambda of a be the sorted list of eigenvalues of a. Consider the following set. I'm fixing an a now. I want to take the convex hull of all matrices that have the same spectrum as my fixed a. This turns out to be a graph invariant convex set also. Convex by construction and graph invariant, one can check. And this set has a tractable semi-definite programming description. So convex, but also tractable to specify, and hence tractable to use in the context of actually solving problems.
If it implies measurization, then scar convex functions you can optimize and find it in polynomial time.
There is a link between majorization and Schur convex functions. That's not what we directly end up using to describe these things. But yes, there is a link there. A set being convex is just a basic definition about, the set being closed under taking line segments or whatever. But not every convex set is tractable to describe. And depending on the set under question, if it's easy to describe, then you have an easy solution method in principle for it. If it's difficult to describe, then you're out of luck. So if your point is, well, we had something convex before, what has changed? Everything has changed. My point is that writing something convex by itself is trivial. We wrote, an exact convex reformulation of graph at a distance. But that doesn't make that problem tractable. What convexity bought you, though, is that it forced you to think only of convex things and you build off of that paradigm. But now you're focusing on writing down easy convex approximations rather than sticking with the difficult formulation. So the distinction I want to make is not between combinatorial or non-convex and convex. Everything is convex, like I described in the previous lecture. The distinction is between difficult and tractable convex things and easy tractable convex things.
My question was, for example, in this example,
Yeah?
why is it easy to describe? Like, what is so special about these eigenvalues and things like that make it easy to describe?
I can go through that offline, but yes, this is, showing this is it's a non-trivial linear algebra exercise. And same thing with the previous case too. But yeah.
And when you say it is easy to describe, do you mean instead of having exponentially large number of...
Precisely. There'll be a polynomial in n size description of this thing using linear functions and semi-definite inequalities. That's it, yeah. So here is an example of a convex graph invariant that is hard. We all know the max cut problem. It will give us a convex graph invariant that is in fact hard to compute because max cut is NP hard to evaluate in general. But we'll see how one can write down simpler things. So a graph cut is something that partitions the vertices of a graph into two subsets, right? And the value of any cut, the value of any such partition, is the total edge weight between the two subsets of vertices. So here is an example of the Peterson graph where I'm putting the outside vertices in one subset and the inside vertices in another subset. And the red edges represent the things from one subset to the other. 5 would be the size of this cut because there are 5 edges from one subset to the other. In general, searching over all possible cuts to identify the largest sized cut, if you will, is NP-hard. One of the well-known NP-hard problems. Nonetheless, the max cut value of a graph that is specified by an adjacency matrix A, up to scaling and shift, is given by this expression. And this is a graph invariant convex function. So somebody else also, you were talking about gradient descent, right? Well, this is a function that's a convex function. Easy to check that it's a convex function. But you can't even evaluate it, much less compute gradients or anything like this. This function of A is a convex function. But if I give you a particular A, for you to return for me the value of this is not easy in general. So being able to say we can apply gradient descent assumes a lot, for example. So the graph invariant convex function, NP hard to compute, but there are standard relaxations for this, this function that are convex, that are graph invariant, and that are tractable. This is a standard STP relaxation of this function. Again, you plug in an adjacency matrix A and out comes a number. But this is easy, whereas this one is difficult. Okay? It is not exact, yeah, it is in general. I mean, there's a rich literature on this topic. People have carried, it turns out that here I'm optimizing over a larger set compared to this. So the value of this quantity will be in general bigger than or equal to the value of this quantity. But by how much is a, is a topic that's been sort of thoroughly investigated at this point, specifically for the max cut problem. So you can write down, this is a convex thing, but hard. This is a convex thing derived from this hard thing, but that's easy. The point I want to make is that writing down convex things is not a big deal. Writing down easy convex things is a big deal. And so if you wanted to, in whatever graph problem of interest, constrain the cut value of the graph, the max cut value of the graph to be something, to be at most something, you would not be able to use this because it's not computationally efficient, but you would be able to use this at some loss of accuracy. Yeah. This loss of, say some loss of accuracy, but we will do two things as we go along. One is we'll prove under certain conditions that these easy convex relaxations are actually exact under certain conditions. We'll also show, because these things go in one direction, that this is less than or equal to this in general. Sorry, this is bigger than or equal to this in general. That because they go in one direction, we can get bounds on things like the graph edit distance. So, the edit distance is the smallest number of changes from one graph to get to another graph, but I can obtain bounds on that distance for you because these quantities go in one way. So while it's, an approximation, because it goes in one direction, you can still kind of say these sorts of things. Okay. The last graph invariant, and then we'll get back to our applications. Last convex graph invariant. Something called the stability number of a graph. A stable set of an unweighted graph is a subset of vertices such that every pair of vertices in the subset is non-adjacent. So if I take that graph, the red vertices form a stable set because no two vertices there are adjacent to each other. The stability number of a graph is the size of the largest stable set. And in general, this is also NP-hard to compute. There's a magical result, not the 60s, the 50s, right? 59, yes, close enough. Which says that the inverse of the stability number can be described in this way. So I plug in the adjacency matrix of my graph, and out comes the inverse of the stability number, meaning 1 over the stability number. But this is interestingly well defined for any symmetric matrix. So, you can sort of, if you plug in a 0, 1 matrix corresponding to an unweighted graph, you'll get the honest inverse of the stability number. But this is a well-defined object over all of Sn, which is very useful for our purposes because when you want to define convex or related functions, you want to be able to define them over all of Sn. Right? So this is a graph invariant concave function, negative of a convex function. NP hard to compute because if I could compute this easily, I'd be able to compute stability number easily, and that's a problem because we know that that's NP hard. And again, you can write down a tractable relaxation of this hard concave thing to get an easy concave thing, and that's this. And again, this approximation goes one way. It's a bound in one way, and so you'll be able to. In this case, it's a lower bound, where previously we had an upper bound. And so, in the context of applications, that is relevant.
Why is it called stable set?
Why is it called stable set? It's called, also called like, independent set. That's the
Optimization and Convexity.
Yeah. The Motzkin-Strauss people called it stability number and inverse stability number. I wrote stability number only because it's shorter to write and fits in a slide compared to independent set. But it's the same thing as independent set. So max weight independent set and so on. This would be the same thing. Okay, so let's get to the planted subgraph problem. Again, writing down a hard convex thing is not a big deal. Writing down an easy, tractable, computationally efficient convex thing and showing that it's useful is where the challenge is. When you say it's bad, what do you mean?
Integrity gap would be
Integral, yes. This, in that sense, it could be bad. But, there's lots of perspectives here. One is, I exactly want to solve a problem. Under what conditions can I do this? So those are conditions where you care about integrality gap. There are other situations, and we'll see this particularly with graph at a distance, where bounds are all that, bounds already sort of are very interesting and get you interesting consequences in the context of applications. So there, this is already kind of relevant and useful. So planted subgraph. Recall that we had, a k by k, a k node graph with a k by k adjacency matrix for some small graph h, and ag for a larger g. Recall that our first convex program that we wrote down, the intractable thing, was this. Right? One natural thing you could do is to say, I'm going to relax the intractable convex constraint further by only using spectral information about my graph. So rather than taking the convex hull of, permutation times this times permutation transpose, I'm going to take the convex hull of orthogonal times my graph times orthogonal transpose. That's effectively what this is. And this thing, as we saw a few slides ago, has a tractable semi-definite programming description. I think there was somebody who asked something about Shor functions. It actually has connections to the Shor-Horn theorem, and that's why we call this the Shor-Horn relaxation. So this is a relaxation. This set is an outer approximation of this set. It continues to be convex. It's easy, unlike this set. And this is a semi-definite programming problem. This is a tractable semi-definite programming problem. So you can solve this and ask when it might work, right? So we had a hard combinatorial thing. We reformulated it via a hard convex thing. And now we've approximated it, relaxed it, by an easy computationally tractable convex thing. So that's the flow of logic here. Yeah? That's one way to think about it. It's not always the case that any discrete thing is difficult and continuous is easy. So that's not true. But in this particular case, replacing permutations by orthogonals makes things easy. Yes. Yeah.
So I believe this problem's solution would be like an upper bound but not problem solution.
Correct. Yes, in general.
And do we have bounds like how far they are?
I'll get bounds in the context of graph edit distance. Here, I won't be worrying about bounds. I'll be more interested in identifying conditions when this actually exactly solves this problem. In general, we shouldn't always expect this to solve this problem, but under what conditions is that true? Okay. So that's sort of the thinking for the next few
The purpose
slides.
of asking this question is you have used these spectral invariants. I could have used some other thing.
Absolutely, absolutely.
Why is this better than maybe some other?
So, great question. And that's actually, as far as I'm concerned, an open question. I don't know. If you told me that AH has this kind of structure, I don't have a good answer to the question of what are the best invariants to use for that structure. What are the best ones that are tractable to compute, but also sort of best reflect the structure of that graph? Here, I'm going to go through the opposite exercise. I'm going to stick in this relaxation and then try and tell you for which graphs it actually works. So it's, an exercise in the opposite direction. But ideally, what you want to be able to get to is, hey, I have a particular graph H. What are the best things you can write down for this graph? And for that, I don't have a good answer. Yeah.
A follow-up question. Can we say that whatever invariant that helps relax, we won't be able to do better than this? Do we have answers to such questions?
You should not be able to say that because, in general, this problem is NP hard. So I don't know what you mean by not do better. You can always, write down this. That's a hard convex set, right? So I don't know what you mean by not do better.
Like LP and SDP. So SDP is kind of stronger than LP.
This is an LP.
Right. So
This one up here is an LP.
yeah, similarly, maybe it's a spectral invariant, there is some other invariant which is strictly stronger or as strong as spectral invariant, but maybe it's hard in general. Like there's some intermediate relaxation between spectral and the general problem.
That's true, but my point is this is already an LP. If you're thinking of LP as easy and SDP is hard.
Not LP, but some invariant. So spectral invariant, if
Yes.
some other invariant, maybe that is stronger compared to spectral. It's just some
So
kind of
really what you're wanting to say is, can I add extra constraints here? That, can I say X belongs to this spectrally constrained set? X also is constrained in terms of max cut value. X is also constrained in terms of stability number value. You can start doing that. You can sort of put lots of constraints here. And we'll see the value of that in the graph edit distance problem. But in general, yes, you can keep on padding more and more constraints here. Here, I just want to add one thing and show you at least some situations where it's interesting and connect to the existing literature. So it's more about that than something magical about projection. In fact, I would say take a simpler problem than projection. I want to optimize a linear function over the set. That's in general hard. That's even simpler than projecting a point, computing a Euclidean projection of a point onto the set, right? And that's hard in this context. Yeah. Mm-hmm. So this is tractable. We call it the Schur-Horn relaxation. One question is, well, when is it exact? When does it actually solve the original problem, right? To get to when, so again, we're proceeding in the opposite direction. We write down a solution method and ask when it works, right? Rather than developing a solution method that's tailored to a specific problem, if you will. But here, we actually have an interesting and nice answer to this question. And to get to that answer, we need a definition. So this is maybe the second definition of this talk and second and last one. So two matrices, symmetric matrices, n-man symmetric matrices, will be called spectrally comonotone if there exists an orthogonal matrix such that when I conjugate both of them by the same orthogonal matrix, these are diagonal matrices with sorted entries. How many of us know what simultaneous diagonalizability means? This is a property where when I have two matrices, they're called simultaneously diagonalizable. If when I conjugate them by orthogonal matrices, I get diagonal things. That's simultaneously diagonalizable. Here I'm asking for something more. I want diagonal things, but where the entries are sorted also. Okay? Sorry?
Do you require Y and Z to be PST?
Just symmetric. Just symmetric. Yeah, but symmetric matrices have real eigenvalues, so yeah. So this makes sense. Yeah. Okay. And it's more restrictive than simultaneously diagonalizable. Okay, and informally, and we'll have a theorem that says formally what happens. This previous relaxation that I wrote down succeeds when the planted adjacency matrix has many matrices with which it is spectrally comonotone. Okay? So if you back out of that, what's actually going on? We want this planted subgraph to have very few distinct eigenvalues. So it's a graph on k nodes, right? That was the notation I used. So it should have far fewer than k distinct eigenvalues. So lots of multiplicities in the eigenvalues. What's a graph that has lots of multiplicities in its eigenvalues? Sparse graphs, not in general. The clique is an example of a graph where if you look at its adjacency matrix, it has two distinct eigenvalues, no matter the size of the clique. Okay? And if you look as a result at the planted clique problem, that's a specific specialization of this question that's been studied in the literature, that property is used extensively. Although people don't write it that way, that's really used extensively, that it has just two distinct eigenvalues. But this method will work for lots of graphs that have few distinct eigenvalues. So we'll show that it works for the planted clique problem, but it works if the planted graph is any of these and many, many more. And this is in fact a significant topic in graph theory. What are graphs that have few distinct eigenvalues? For now, the actual scaling laws that you can write down will depend on scaling, how many you have relative to graph size and so forth. Okay, so we have a theorem. I can go through the details of this theorem, but sort of more than that, I want to go to the experiments so we can see some interesting results. But there is a theorem that formally describes, in an Erdos-Renyi type model, when this does something interesting, we can give guarantees on exactly when this method succeeds. But I want to actually describe some experimental results. We recover prior results for planted clique type problems. And some of the conditions in the theorem were not completely essential. I know I went through it quickly, but I'm happy to talk about this stuff offline. But I want to actually get to some examples. Okay? So here is something called the Klebsch graph. This is this graph that we had right at the beginning. This is a graph on 16 nodes, and I've planted it inside a graph consisting of 50 nodes. The Klebsch graph is 40 edges. This larger thing is 130 something edges. What's special about the Klebsch graph is that it has 3 distinct eigenvalues. So even though it's a 16 node graph, and in general you should expect it to have 16 eigenvalues, it only has 3. That's what's special. And n here is the size of the larger graph in which I've stuck the Klebsch graph. P is the probability of an edge in outside of this Klebsch graph and this larger n node graph. Okay? So P will vary between 0 and 1, and then can go quite a bit up. Okay? Similarly, here is a 27 node graph planted inside a graph consisting of 100 nodes. And this is an example where we exactly figure out where this 27 node thing is inside this 100 node thing. If I show you this matrix, you can look at the blues and the reds, and it's easy, but in general, you don't have access to this. And you can go on and on. These are all graphs, by the way, on, previous was n equals 27, k equals 27 vertices, 28 vertices, but again, 3 distinct eigenvalues, 36 vertices, 3 distinct eigenvalues, and so forth. Even just focusing on the case of 3 distinct eigenvalues, the clique is 2. It's the only graph that has 2 distinct eigenvalues, only connected graph that has 2 distinct eigenvalues. Going to 3 itself is already a very rich story. Graphs with 3 distinct eigenvalues that are regular are called strongly regular graphs, and there's a rich kind of, there are entire books on just that topic. But yes, you can kind of go through this, each of these examples. Yeah, go ahead.
So phase transition formula, some theoretical guarantees when this.
Yeah, this is examining, this phase transition involves n, the larger thing into which I'm planting my graph, and p, the probability of a noise edge. And this theorem, which I quickly flashed, has these sorts of scaling things. So under certain conditions, you can write down theorems like this. This is not even the most general theorem you could write down, but this is the ease. Yeah.
Now the question is always looking into H, but not into G. So
G, at least for these experiments and for that theorem, is Erdos-Renyi. Outside of H, the edges are, placed.
Another question that, given some kind of G, is it easier to find some, H or something like? Even the structure of G might be.
Absolutely, that could matter. The theorems that we have don't say anything about this, but that's very much a good question. Part of the reason we went with this model is that this was the model used for planted clique. So we said, okay, let's do the same thing here. But no, that's a very good question. All right. So here the experiments that I showed you were sort of a stylized nature, right? We picked these graphs and showed you what could be done. Here we'll actually show some real examples with the graph at a distance problem, and we'll conclude in about 5 minutes or so. Okay? So again, recall that we have adjacency matrices corresponding to 2 graphs, G1 and G2. We're going to assume that G1 and G2 are graphs on n vertices. And for simplicity, again, only edge additions and deletions, no vertex stuff. Okay? The first convex program that we wrote down, again, exact but intractable, was this. Sum of the absolute values, this stuff. This is what we wrote before. And this set in red is the hard set. And here we'll consider relaxing our intractable constraint using all of these. We'll use the spectral stuff, we'll use max cut, we'll use inverse of the stability number. We'll throw all of these in. Each of these are outer approximations of this red thing. Okay? Yeah?
This problem is symmetric in G1 and G2.
That's right. Yes. What you should have in mind, though, is that if one of the graphs has a bit of structure, then that's the thing you designate as G1 and so forth. Yeah. But that's very good. This is symmetric, but I've not written it in a symmetric way here. Good question. These are all outer approximations of this set, right? So what should you expect to happen if I tell you that this is exactly the graph at a distance? This problem, if you solve it, it's hard to solve, exactly computes the graph at a distance. Now if I replace this red constraint, the hard one, by outer approximations, what should you get? You're minimizing over a larger set, so you should get a lower bound on the graph at a distance, right? And that is significant because for any relaxation we would put here, anything, you're going to get lower bounds on the graph at a distance. So you are going to get numbers out of these relaxations that say you at least need to make 10 changes to go from graph G1 to G2. So this is a situation where, of course, exactness and so forth, no integrality gap and so on are interesting. But the fact that you're actually able to produce lower bounds is already an interesting property. With respect to each other, these in particular are unstructured. I mean, they will, it's not that one, they're all outer approximations of this thing, but they, are not, it's not that one is contained inside the other or anything like this. Yeah. Okay? And this is actually very interesting in the graph at a distance literature, because if you look at the existing literature prior to this work, it mainly considered upper bounds. So if I develop a heuristic for you, some method to go from graph G1 to graph G2, I do some combinatorial search, and I get you from G1 to G2. What is that quantity giving you? What is that heuristic giving you? It's giving you an upper bound on the number of edits I need to make to go from G1 to G2. So every heuristic out there for graph at a distance is giving you upper bounds. So they focus on getting some sequence of edits to go from one graph to the other graph. And there's essentially little to no work on the lower bound problem. You at least need so many edits to go from one graph to the other graph. So this is a situation where, you do care about the quality of the lower bound, but the fact that you have a lower bound is actually already interesting. Right? And so you could use this convex framework to actually look at the quality of any upper bounding heuristic. An upper bounding technique might give you some number. You can use this convex method to get a lower bound and see how well that upper bound actually did. Right? And so here is an example, a real example, involving molecular structure comparison, where we combined all of these invariants. We stuck in all of them. You can take the intersection of those things. Each individual one is easy, so the intersection of 3 of them is easy. And we applied it to a data set that consists of 94 molecules, each represented as a graph. And what was done is every pair of molecules, i.e. every pair of graphs is taken. That's 94 choose 2. And we applied, I think, something called the A-star algorithm, or an existing heuristic for computing graph at a distance. And we took an average of these upper bounds over 94 choose 2 pairs. Okay? That gave us the number 29.8. We have no idea if this upper bound, this is the average upper bound produced by existing heuristics. We don't know if it's exact, right? Using all those 3 together in the same context, 94 choose 2 pairs, we looked at lower bounds and the average lower bound, and that was this. There are, of course, some cases, individual pairs, where the 2 might match, in which case you're done. But it's saying that at least on this data set, you're at most about 2/3 off with this technique, right? With the upper bounding technique. So this is how convex relaxation can actually help you, by producing lower bounds in a computationally tractable way. Yeah?
So you can have more constraints like Lassé hierarchy or like.
I can put 1,000 other things here. Yeah, and at greater computational expense, you can get tighter and tighter lower bounds. You can prove that eventually you will get to the actual graph at a distance for sure, but that will require in general.
But 3 was already good enough for your.
These 3 that we put, I don't know what you mean by good enough. It gave us this number, right? You can try and add some more, maybe it gives you a little bit more, who knows, right?
But individually, if you were only spectral or only maxcut, then the number was good.
I think only spectral did reasonably. It gave us 18 or 19 or something. Only max cut and only inverse stability gave us much lower values. Yeah. So this is the sort of thing that this framework can do for you. actually produce lower bounds that tell you that an upper bounding technique is reasonable, not reasonable, or how much you've lost. So here too we have a result. Imagine only using spectral invariants. So this is the only constraint we have, eigenvalue-based constraints. Then there is a theorem that goes as follows. This is an easier theorem to digest somehow. Suppose G1 is the thing we're sticking into this constraint. So there was a question about whether our formulation is symmetric. It's not symmetric, but if you know that one of your graphs is a little bit of structure, that's the thing that you would stick into the blue thing, right? In this case, the structure we're assuming is few distinct eigenvalues, again, because that's when we know that this kind of relaxation does something interesting. And this is a situation where G1 is a graph with few distinct eigenvalues, and based on the multiplicity of the second highest multiplicity eigenvalue, you can do very refined analysis to get bounds of this type, where D is the number of edits that get you from G1 to G2 per vertex. So if I take G1 and I perturb at most D of the edges, either add or remove per vertex of G1 to get to G2, and I plug that into this formulation, then the above relaxation is tight and will actually give you the graph edit distance rather than just a lower bound on it. So you can go through this sort of a theorem proving exercise with the other invariants also. There are some situations, interestingly, where it gives you optimal results. So the family of Johnson graphs, parameterized in this way, are graphs over M choose L many vertices, where you should view the vertices as L element subsets of M items. That's what M choose L means. And you have edges between vertices that share L minus 1 items. And our result, if you specialize it to the case of Johnson graphs, says that you can tolerate so many edits per vertex of a Johnson graph and still recover the Johnson graph back. So if G1 is a Johnson graph, and you have so many edits per vertex that you make to get to G2, you can plug it into our formalism and you can get the Johnson graph back. And this is optimal when L equals 2, because the degree of this Johnson graph is n to the 1/2. So I'm saying on the order of the degree of that graph can actually be perturbed and you still get the Johnson graph back. You should not expect to do any better than this. So in some situations, this relaxation is not just tight, but sort of as good as you can possibly hope for. And you can get similarly precise results in a bunch of other situations. Okay, so let me wrap up. I talked about convex graph invariants. I think it offers a systematic way to think about convex relaxations for hard inverse problems on graphs. If you look at some of the proofs of these theorems, there's very interesting links between geometry, convex geometry in particular, where vertices, boundary structure of a convex set and so forth, and graph structure, which is inherently combinatorial. There are lots of further questions. In particular, if you give me a specific graph or a specific graph structure, and you ask me for this graph, or for this kind of graph structure, what is a convex invariant that is optimal in some sense? I don't even know what I mean by that, but that's also computationally tractable. This is sort of one of the questions that was asked along the way. This we don't have a good answer to. We know good relaxations to write down that are tractable, and then we can try and work out when it's actually useful. But the other direction, which is you hand me a graph that you actually care about in the context of an application, what is a good convex invariant for that graph structure? I think, we don't have a good answer to this. There are other situations where, these are maybe pet topics that I've spent a lot of time thinking about. They show up in some applications, but they're maybe more of mathematical interest. But convex invariants for forbidden minors is an interesting sort of question that I don't have very much to say about. But from the perspective of an application, from the perspective of applications, question one is the interesting and relevant one. Anyway, thank you. I'm happy to talk about any of these things offline.